Here's your Sioux Falls physics teachers looking more at capacitors and circuits. And this problem is a series circuit with two capacitors of unequal capacitance. Again, our first step will be to draw a circuit diagram of the situation. First, we'll insert the battery, two lines of unequal length. For the capacitors, we need two pairs of lines of equal length. And again, notice that since they are in series, we need to have them one after the other. So we would follow the wire first to the first capacitor, which is 4 farads, then to the second capacitor, which is 6. The voltage of the battery is given as 12 volts. First thing in this situation that we will need to do is find the equivalent capacitance. And part of the reason that we need to do that is because we really don't know at this point how much of each of voltage is on each of those capacitors. So for a series, remember that our capacitance decreases, so we would use the equation with the inverses, and that would lead us to 4 plus 6 to the negative first. That means that the equivalent inverse is 0.42, giving us an equivalent capacitance of 2.4 farads. Now again, that's not really one of the final questions that is asked, but we will need that value to be able to find the rest of our answers. Once we have the equivalent capacitance, then we can go back to our equation of capacitance equals charge per volt and use this to analyze the entire circuit. So our equivalent capacitance was calculated at 2.4. Our charges are unknown, and the total voltage for the circuit is 12 volts. From that, we can find that the equivalent charge stored in the circuit is 28.8 coulombs. Now notice that even this is not actually one of the questions, but it asks to calculate the charge stored on each capacitor. Well, for a series circuit, remember that one of our statements is that the charge stored on the total circuit is the same as the individual charge amounts. So even though we have solved this using equivalent amounts for the entire circuit, it is also true to say that that is the charge stored on the first capacitor and the charge stored on the second capacitor. So both of these capacitors, even though they have different capacitance amounts, they must both have the same amount of charge. The last part then is to find the potential difference across each capacitor. And now that we know how much charge is on each, we can simply go back to our equation of capacitance equals charge over volts and plug in the numbers for the individual capacitors. So the first one has a capacitance of 4 farads. It is storing 28.8 coulombs, and that gives us a voltage value for the first capacitor of 7.2 volts. Secondly, we have capacitor 2, which is 6 farads. It also is storing 28.8 coulombs, and its voltage value then turns out to be 4.8 volts. So our individual amounts are 7.2 and 4.8. We can double check that those are reasonable, because if added together, they do give us a total for 12 volts for the circuit. Also notice that the difference in voltages are necessary in order for us to be able to have the same amount of charge stored on two capacitors with different values for capacitance. So in other words, our first capacitor here has a pretty low capacitance value. So in order for it to have the same amount of charge as this capacitor, we need more volts on the first capacitor and fewer volts on the second. Hey everyone, here's your Sioux Falls physics teachers, and today we're going to look at a more complex circuit. Again, these types of problems do look rather tricky to begin with, but once you get the steps down, you see that it's actually a pretty repetitive process. So here we have a complex circuit. We have 8 microfarads, and then that's in series with a combination of 4 and 2. The first thing that we want to do is actually label these capacitors to make it easier for us to determine what we're talking about. So we'll label the first one here as C1, the second two as C2 and C3. And our first task then, it says to determine this charge stored on each capacitor. Before we can do anything separately, we need to find the equivalent capacitance for the entire circuit. So our first step will be to start with the smallest combination. So notice that before we can do anything involving C1, or the 8 microfarad capacitor, we need to deal with C2 and C3 because they are connected to each other. They are connected in a parallel arrangement. So the first thing that we'll do is find the equivalent capacitance of these two together. And notice that it can be helpful to actually write capacitance 2 and 3. So we remember which two we're dealing with. For parallel, this would be simply adding together. And again, remember one of our hints is that we don't need to convert out of microfarads. So capacitance 2 and 3 is simply 6 microfarads. Now we're ready for the equivalent capacitance of the entire circuit. Basically, when we look at our diagram here, we can now consider this portion to be as a single 6 microfarad capacitor. So in essence, what we have is an 8 microfarad capacitor in series with a 6 microfarad capacitor. For series, again, we use the inverses. So we're going to take the inverse of C1 and the inverse of 2 and 3, which we just found. That's 8 microfarads and 6 microfarads. And we find that the inverse then of the equivalence is 0.29, and that means that our overall equivalent capacitance is 3.4 microfarads. Now our next step is going to be to find the total amount of charge. And for that, we'll go back to our definition equation for capacitance and apply it to the entire circuit. So we have our equivalent capacitance of 3.4 microfarads. We will be looking for charge, and our equivalent voltage is 6 volts. From that, we can solve the total charge, or the equivalent for the circuit, and we find that we get 20.6 microcoulombs of charge. Again, notice the advantage of not switching out of the micro label for farads. We can simply attach it now to microcoulombs. Notice that still what we're looking for is the charge on each capacitor, and this is labeled as the charge equivalent for the entire circuit. But remember that now our circuit basically consists of an 8 microfarad capacitor in series with a 6 microfarad capacitor. And for series circuits, The equivalent charge is the same as the individual amounts. So this amount here, the 20.6 microcoulombs, is also the same as the charge stored on capacitor 1. So we have found one of our final answers. Now it is also the same as the charge stored on capacitors 2 and 3 together, which is going to be useful to us. It doesn't tell us how much is on each one individually yet, but we can use that fact then to break down the amount of charge that is on each one. Before we do that, we will need one more piece of information, and that is the voltage amounts. So in order to do any calculations with 2 and 3 individually, I need to know how much of that 6 volts is acting on 2 and 3. So we will start then by looking at the capacitance for 2 and 3 and comparing that to the charge and the voltage. Earlier we found that the equivalent capacitance for 2 and 3 is 6 microfarads. We just found that the charge amount for 2 and 3 together is 20.6 microcoulombs, and we can use that to solve for the voltage of 2 and 3 together. And we end up finding a value for that voltage of 3.4 volts. So if I go back to our diagram over here with our circuit, we have 6 as the total. 3.4 of those volts are acting on this parallel combination. Now we actually could do a little bit of subtraction here if we want to, and we'd find that 2.6 volts must then be acting on this single capacitor, but since we already have our charge amount, there's no need to get that voltage. The reason that this voltage though will be helpful is that now, if that's 3.4 volts, we can now take our capacitance equation and apply them to capacitors 2 and 3 individually. So capacitor 2 individually had a capacitance of 4 microfarads, and that 3.4 volts will be acting on capacitor 2. And we solve for charge and get 13.7 microcoulombs of charge. The last step then would be to take our equation and apply it individually to capacitor 3. Notice that capacitor 3 had a capacitance of 2 microfarads. We are looking for the charge amount, and we will use that same value of 3.4 volts. That gives us a charge for capacitor 3 of 6.9 microcoulombs. So we now have our individual values for all of the 3 capacitors. And notice that if we wanted one final double check, we could compare between capacitors 2 and 3 here. And we could take 13.7 plus 6.9, and we should come up with that 20.6 value that we got earlier as the total for the 2 together. Hi everyone, we've got another complex circuit problem coming your way from the Sioux Falls physics teachers. Again, we have 3 capacitors with a little different arrangement here. 2 and 1 are together in a series in a line, and they are in parallel with 6 microfarads. First of all, we want to determine the total capacitance. Before we do that, again, we will mark off some labels so that we can easily see which capacitor we're talking about. And notice that our first combination to deal with, before we can deal with this little parallel segment, is to take capacitor 2 and capacitor 1 and find the equivalent for those 2. Because those 2 are in series, we will be using our series equation, which involves the inverses. And so we'll be looking at 2 microfarads and 1 microfarad and putting those two in series. We end up with a value for the inverse of 1.5 microfarads, and inverting that value for capacitors 1 and 2, we get 0.67, or 0.6 repeating, microfarads as the overall capacitance for those two. Now we're ready to deal with the total circuit, and remember that basically what this gives us is that these two together can be considered the same as a single capacitor of 0.67 microfarads. To put that in parallel with the 6 microfarad capacitor below is simply an addition problem. So the equivalent capacitance in this case will be the capacitance of 1 and 2 combined, added to the capacitance of capacitor 3, because that combination is a parallel combination. That gives us 0.67 microfarads plus 6 microfarads, and we find that our equivalent capacitance for the entire circuit is 6.67 microfarads as the total amount. Now we can begin dealing with the individual capacitors. And we're going to go ahead and deal with capacitor 1 and 2 first. Notice that those two are together in the same series leg of the circuit. And so if we kind of follow the wire, those two capacitors together have a direct connection to the 12-volt battery. And so what we will do is we will apply, in this case, our equation of capacitance equals charge per volt, and we're going to apply that to capacitors 1 and 2 together. Now earlier we found that those two together give us a capacitance of 0.67. The voltage that they will receive will be the same as the total battery voltage, which is 12 volts. Now we can figure out the charge for the two of them together, and we find that to be 8 microcoulombs of charge. Now notice as I've written it that it's the total for the two together, but remember on a series circuit that is also the same as the charge for the two individually. So right away, once we know that total, that means that there is 8 microcoulombs of charge stored on each of capacitors 1 and 2. Finally, we're ready to deal with capacitor 3, and we can use our exact same equation, only this time we're dealing with just the single capacitor, capacitor 3. Our capacitance there is 6 microfarads, and again, because it is part of a parallel connection, if we follow the wires, that 6 microfarad capacitor has a direct connection to both terminals of the battery. So it will also receive 12 volts as the voltage. Now we can solve for our charge, and we find 72 microcoulombs of charge stored on capacitor 3. Well, hello again. Our final example on capacitance here is a capacitor and looking at the energy that can be stored. First of all, we need to find the capacitance in this situation. Now, we're given the information that we have an area of 0.075 square meters and plate separation of 0.3 centimeters between the two plates. So our first task is to find the capacitance, and our equation that gives us that value in terms of the geometric information of the plates is the permittivity times the area divided by the distance. Again, permittivity is a constant that can be found on your data sheet, and it's 8.85 times 10 to the negative 12. Area, 0.075 square meters. And distance, changing into meters, is 0.003 meters. From that, we find a value for capacitance of 2.2 times 10 to the negative 10th farads. Next, it asks to calculate the charge stored on this capacitor when connected to 12 volts. So for that, we'll go back to our definition of capacitance, which is the amount of charge per volt. We have our value of 2.2 times 10 to the negative 10th. And this is now connected again to a 12-volt battery. And solving for the charge, we find that it is 2.7 times 10 to the negative 9th coulombs of charge when connected to that battery. Next, we'll calculate the energy amount. And again, remember a couple of things that you are looking for. First of all, we're looking for the energy stored in a capacitor. So watch for that C subscript. And then there are two versions, both of which we could actually use because we've calculated both amounts by now. But the first version is probably the simplest given the information that we have, which is simply 1/2 times the charge times the voltage. We have already calculated the charge at 2.7 times 10 to the negative 9th coulombs. We have calculated or been given the voltage at 12 volts. And completing that problem, we find 1.6 times 10 to the negative 8th. We are measuring energy, so this is a measurement in joules. And again, there is a second version of the equation. It would be using directly from the capacitance and the voltage, and barring any little errors from rounding and such, we should have received the same answer if we use that as well.